It feels like every time you turn around, there's a new breakthrough in large language models.
Yeah, absolutely.
Keeping up with it all can feel like you're constantly sprinting just to stay in place.
Mm-hmm.
So that's why we do these deep dives,
That's right.
where we take the research papers that are really pushing things forward and kind of distill out the most interesting and most important parts.
Exactly. We try to cut through all the noise and highlight what really matters.
Exactly. So for anyone listening, if you just want to get a handle on what's actually significant without having to wade through every single paper yourself,
Yeah.
that's what we're here for. And for this deep dive, we're going to be looking at something particularly fascinating. Uh,
Yeah.
it's a paper all about making these massive language models actually run more efficiently, which is
Oh,
a
huge.
huge problem because as they get more powerful, they also get
More expensive. Yeah.
more expensive, more resource intensive.
Yeah.
So the paper we're looking at today is called FN Fusion, Rethinking Sequential Computation in Large Language Models.
Catchy title.
Yeah, and along with the paper, you've also provided some really helpful supplementary notes.
Yeah, just to kind of put it all into context a little bit.
Perfect. So our mission here is to really understand this kind of new idea of FFN Fusion and see if it can live up to its promise of basically revolutionizing the way we run these LLMs.
Yeah, it's about going beyond just making these models bigger and bigger
Right.
and actually figuring out how to make them more usable in the real world.
Absolutely. So anyone who's been following along with LLM developments will know that it's amazing what they can do. But at the same time, there's always this elephant in the room, which is
The sheer computational cost.
exactly,
Yeah,
and that's exactly what the introduction of this paper really focuses on,
it does.
right? They talk about how these escalating costs are becoming a barrier
Okay.
to wider adoption to people actually experimenting and using these things.
Yeah, you need these massive server farms and, huge budgets just to get started.
Exactly. So it's not really accessible to
Everyone, right?
most people. So the paper talks about some of the ways that people have already tried to optimize these LLMs, things like quantization, which is basically using lower precision numbers in the calculations.
Right, like instead of using a full 32-bit floating point number, you might use a 16-bit or even an 8-bit representation.
Right.
It saves memory and bandwidth, but the trade-off is,
Potentially losing accuracy.
yeah, you're sacrificing a bit of precision.
Then there's preening, where you're trying to remove redundant connections within the network.
Right, the idea is that those connections aren't really contributing much to the final output.
Right. So you can just get rid of them and have a smaller, more efficient model.
Right, but finding those redundant connections gets harder and harder.
The more optimized the models already are.
Exactly.
And then, of course, there's the mixture of experts approach, or MO.
Yeah, which is a really clever idea.
Very clever.
Where you only activate certain parts in the network depending on the specific input.
Right. So you're not using the whole massive model for every single task.
Exactly. But the paper points out that for smaller tasks, or if you're not working with huge batches of data,
Right.
it might not give you the speed gains you'd expect.
So this is where FFN Fusion comes in. And this is where it gets really interesting because FFN Fusion takes a completely different approach.
It does.
Instead of just tweaking things around the edges, it really questions this fundamental assumption that transformer models have to process information in this very linear, sequential way.
Right, like a factory assembly line.
Exactly, layer by layer in a very strict
Yeah.
order. So FFN Fusion basically says, hold on, is this sequential processing really always necessary?
Interesting.
Especially when you look at specific types of layers like these feed-forward network layers or FFNs.
And they often come after you've removed some of the attention layers, right?
Right, and that's a key insight that you highlighted in your notes, that after certain attention layers are removed, you might find these sequences of FFNs that could actually be run more independently.
Yeah, there's less dependence between them.
So instead of each layer waiting for the previous one to finish its calculations?
They could potentially work in parallel.
Exactly, and the paper's figure 1 is a really good visual representation of how this two-step process works.
Okay.
The first step uses something called puzzle. What exactly is puzzle?
Well, it's this really cool neural architecture search framework.
Okay.
Think of it like an AI architect
Okay.
that can automatically figure out the most efficient structure for a neural network given a specific task and the hardware limitations you're working with.
So in this case, the goal of puzzle is to take this big LLM and essentially optimize it for inference.
Exactly. Make it run faster and use less resources when you're actually using it to generate text or do whatever you want to do with it.
Right. So it's not about making the model smaller for the sake of being smaller.
Right.
It's about making it more efficient for the specific purpose of inference.
Exactly. And to achieve that, puzzle might do things like selectively remove certain FFM layers or even entire attention layers if it determines they're not crucial for efficient inference.
So it's like streamlining the architecture intelligently.
That's a great way to put it.
And then the second step is where the actual FFN fusion comes in.
Right.
So we've got these consecutive FFN layers, especially the ones that Puzzle has identified as being good candidates.
Yeah.
What happens next?
Well, the idea is to take those consecutive layers and merge them into a single, wider FFN layer.
So instead of having, let's say, 3 FFN layers processing one after another,
You have one bigger layer that can handle all of those calculations in a more parallelized way.
much more efficiently. So is that mathematically sound? Like, are we actually allowed to just merge these layers together without messing everything up?
That's a good question, and thankfully the paper addresses that directly.
Okay, good.
Theme 3.1 and Appendix A lay out the mathematical foundation for FFN fusion.
Okay.
They demonstrate that the function performed by a sequence of FFN layers can be exactly replicated by a single FFN layer with the weight matrices combined in a specific way.
So it's not just a hand-wavy idea, there's actual math backing it up.
Exactly. It's a mathematically rigorous transformation.
And importantly, this holds true for common FFN variants like switchel U.
Right, because that's what they used in their experiments.
Okay, so we've got this mathematically sound way of fusing these layers, but what's the practical benefit? Why go through all this trouble to fuse them in the first place?
The real efficiency gain comes from how these large models are run on distributed computing systems. Okay, often using something called tensor parallelism.
Tensor parallelism.
Yeah, imagine you have this complex calculation that's too big for a single GPU to handle.
Okay.
So you split it up and distribute it across multiple GPUs.
Okay.
Now, in a traditional sequential model,
Right.
after each layer, there's a point of synchronization.
Right.
All the GPUs have to communicate and share their results before moving on to the next layer.
So it's like a bottleneck.
Exactly, and this communication overhead can really slow things down.
So how does FFN Fusion help with that?
By merging multiple FFN layers into one, you're significantly reducing the number of those synchronization points.
So there's less waiting around.
Right, the DPUs can do more work independently before they need to sync up.
And there's another benefit, right?
Yeah, GPUs are generally more efficient when they're performing larger matrix multiplications.
Right.
So by creating these wider fused FFN layers, you're essentially giving them bigger chunks of work to do.
So better hardware utilization.
Exactly, you're making the most of those powerful GPUs.
And the paper's figure 10 really illustrates this whole idea of reducing synchronization overhead and increasing computation per GPU.
It's a great visual.
So this is all very clever in theory, but does it actually work in practice?
Well, to find out, the researchers put it to the test.
Okay.
They took a massive language model and applied these techniques to create what they call Ultra 253B base.
Ultra 253B base. Okay.
And this model is really the star of the show.
So what's so special about it?
It starts with Llama 3.1405B instruct.
Okay, that's a mouthful.
It is a model with a whopping 405 billion parameters.
405 billion, that's huge.
That's massive.
Okay.
And they ran puzzle on this behemoth to streamline the architecture, and then they used FFN Fusion, and what they ended up with was a model with 253 billion parameters.
So a pretty significant reduction in size already.
Right off the bat.
Just from applying puzzle and FFN Fusion.
Exactly.
Okay, so it's a smaller model, but what about the speed and cost improvements they were aiming for? Did they actually achieve those?
Oh, absolutely. The paper highlights some really impressive gains.
Okay.
When processing data in batches of 32, they saw a 1.71x speedup in inference latency.
1.71x, that's pretty substantial.
Yeah, and what's even more impressive is the 35x reduction in per token cost.
Wow, 35x, that's huge.
Yeah, so you're getting a lot more bang for your buck.
That's a massive improvement.
They also managed to reduce the memory footprint of the KIF cache by a factor of 2.
And remind us again what the KIF cache is?
Oh, right. It's basically where the model stores information about the text. It's already processed. Okay, so a smaller key cache means you can handle longer sequences of text more efficiently.
So all those efficiency improvements are amazing.
Yeah.
But the big question is, does it actually work? Like, did they sacrifice performance to get those gains?
That's the key question, right?
Yeah.
And the results are really promising.
Okay.
Ultra 253B base performed really well across a variety of challenging benchmarks,
Okay.
like Arena Hard Human Evil MLU Instruct MMLU Pro MT bench.
So it wasn't just faster and cheaper.
Right.
It was still able to hold its own against other top-performing models.
Exactly. It's not just a matter of speed optimization.
Right.
FFN Fusion seems to unlock a more efficient way of achieving a high level of intelligence.
So how did they actually create this Ultra 253B base model? Like, what were the steps involved in transforming that original 405 billion parameter llama model?
It's all outlined in section 4 of the paper, along with the timeline in your notes.
Okay.
The first step was running puzzle on the original Llama 405B model.
Okay.
But they gave puzzle-specific targets. They wanted a 1.5x improvement in latency, and they wanted the model to fit within their hardware's memory capacity.
So they were setting some pretty ambitious goals.
Yeah, but puzzle was up to the task.
Okay.
It came back with a 253 billion parameter model.
Okay.
But the key thing was that it had a sequence of 50 consecutive FFN layers.
50 in a row?
No attention layers in between, just FFN after FFN after FFN.
And this was perfect for FFN fusion.
Exactly. This long block of FFNs was right for merging.
Okay, so Puzzle essentially prepped the model for fusion by identifying this long sequence of FFN layers.
Exactly.
So what happened next?
They applied the FFN fusion technique to 49 out of those 50 FFN layers.
49 out of 50? Why not all 50?
Well, their GPUs had memory limitations, so they had to split that long sequence into 4 smaller segments to do the fusion.
Okay, so they couldn't fuse the whole thing at once.
Right.
But what's really interesting that even before any further training...
Okay, this fused model performed remarkably well.
Really?
It was comparable to the baseline model on the MMLU benchmark.
Wow.
And only had a slight dip in performance on MTBench.
So even this radical change to the network structure didn't completely destroy the model's abilities.
Exactly. It's a testament to the power of FFN fusion.
So then how did they get to those really impressive final benchmark scores?
They used a technique called knowledge distillation.
Okay.
It's like a teacher-student relationship,
Okay.
where a smaller model learns from a larger, more capable one.
Okay.
So they trained Ultra 253B base to mimic the behavior of the original Llama 405B model.
Okay.
And they did this using increasing context lengths during the training process.
So the smaller model was basically learning from the best.
Exactly. It was getting a masterclass from the big guy.
And that helped it to recover and even surpass its initial performance levels on benchmarks like MMLU and MTBench.
That's right.
So they were able to push the performance even further.
Yeah, and they didn't stop there. They explored some additional optimization strategies as well.
Like what?
Things like alignment techniques, which is basically fine-tuning the model to be better at following instructions and generating text that's aligned with human preferences.
Okay.
And also just continuing to pre-train the model for a longer time.
So they really squeezed every last bit of performance out of it.
They did.
Now, the paper also goes into this idea of pairwise block dependency.
Yeah.
What's that all about?
So this is about understanding how different parts of the model depend on each other.
Okay.
Like if you change one part, how much does it affect the other part?
Right.
And they use this thing called a dependency matrix to visualize these relationships.
Okay.
And the way they measure dependency is using something called cosine distance.
Cosine distance.
Yeah, it's a way of measuring how similar two things are.
Okay.
So the smaller the cosine distance between two blocks of the model, the less they depend on each other.
Okay, so how does this relate to FFN fusion?
Well, figures 2 and 11 in the paper show these dependency matrices for their ultra-perfusion model.
Okay.
And there's this really clear region where the dependency scores are very low. Okay. And guess what this region corresponds to?
The sequence of FFN layers that they fused.
Exactly.
So that low dependency is why FFN fusion works so well in that part of the network.
Right, because those FFN layers can be fused and run in parallel without messing things up too much.
Because they're not heavily reliant on each other?
Exactly.
But the analysis also shows that there are other parts of the model where the dependencies are much higher.
Especially in the earlier blocks.
Okay.
So parallelizing those parts would be a lot trickier.
So it's not a one-size-fits-all solution.
Right. FFN fusion is really effective in certain parts of the network, but not everywhere.
Now, the paper also looks at applying FFN fusion to a smaller model around 70 billion parameters.
Yeah, they wanted to see if it would work at different scales.
So what did they find?
They experimented with fusing different numbers of FFN layers. Okay. And the results are summarized in Table 4.
Okay.
And basically, they found that even at this smaller scale, FFN fusion can still reduce the effective depth of the model with only a small impact on accuracy.
So it's not limited to those massive 400 billion parameter models.
Right. It seems to have broader applicability.
That's great to hear.
Yeah, it's encouraging.
Now, one question that I had is, if those SFN layers in certain regions are so independent,
Yeah.
why not just remove some of them altogether?
That's a good question.
Wouldn't that make the model even more efficient?
It seems like it would, but Section 5.2 of the paper addresses that directly.
Okay.
They compare FFN fusion with simply removing FFN layers.
Okay.
And Figure 5 shows the results.
Okay.
And it turns out that removing FFN layers is a lot more damaging to the model's accuracy than fusing them.
Really?
Yeah. And the key reason is that FFN fusion preserves the model's knowledge.
Okay.
It keeps all the parameters from those FFN layers. It just rearranges them in a more efficient way.
So it's like reorganizing a library.
Yeah, you're not throwing away any books. You're just putting them on different shelves.
Whereas removing layers is like throwing away books.
Exactly.
Okay, so fusion is a much more intelligent way to optimize the model.
Right. You're not just blindly cutting things out. You're being strategic about it.
Now, another interesting observation in the paper was this sensitivity of the last FFN layer in a sequence to fusion.
Oh, yeah. Section 5.3 talks about that.
What did they find?
They found that fusing the very last FFN layer in a sequence often led to a bigger drop in accuracy.
Compared to fusing the other layers.
Right.
So why is that?
It seems like that final FFN layer plays a unique role.
Okay.
It might be doing something special that the other layers aren't doing.
So messing with it has a bigger impact.
Yeah.
So this is important for actually applying SFN fusion in practice, right?
Exactly. You might want to leave that last FFN layer unfused.
Just to be safe.
Yeah, it's better to err on the side of caution.
So they've shown that FFN fusion works.
Yeah.
But do they have any idea why it works as well as it does?
They do actually. Section 5.4 delves into that.
Okay.
They looked at the functional characteristics of the FFN layers in those attention-removed regions.
Okay.
And they found really interesting the cosine distance between the input and output of those regions was very low.
So the input and output were very similar,
Right.
meaning that those FFN layers weren't making drastic changes to the information.
Exactly. They were making these subtle adjustments.
Okay.
So their hypothesis is that because the individual FFN layers in those regions are making such small changes,
Right.
combining them through fusion doesn't really mess things up too much.
It's like taking a bunch of small steps versus one big leak.
Yeah, and they even found that reversing the order of those FFN layers had a similar effect to fusing them.
Really? So it didn't really matter what order they were in?
Right, which supports the idea that they're functionally quite independent.
That's really fascinating.
It is.
Now, finally, the paper touches on some future research directions, including this idea of block parallelization.
Yeah, that's where things get really interesting.
So what is block parallelization?
Well, the idea is to parallelize not just the FFN layers, but entire transformer blocks,
Meaning?
both the attention mechanism and the FFN layer together.
So taking parallelization to the next level.
Exactly.
But that's a much harder problem, right?
Oh, yeah, because attention and FFN layers are very different beasts.
Right.
And current inference frameworks aren't really designed to handle that kind of parallelization.
But they did do some initial experiments, right?
They did. They used their blockwise dependency analysis to identify groups of blocks that could potentially be parallelized.
And did it work?
Well, it's still early days, but their initial findings suggest that it's a lot more challenging than FFN Fusion.
So FFN fusion seems like the more promising avenue for now.
For sure.
But block parallelizations is definitely something to keep an eye on. So to wrap things up, what are the big takeaways from this research? What are the most important things that the authors want us to remember?
The key takeaways are highlighted in the concluding remarks.
Okay.
First, they found that there's surprisingly little dependency between FFN layers in certain parts of the network.
Which is what makes FFN fusion possible.
Exactly.
And second, they found that the last FFN layer in a sequence is particularly sensitive to fusion, so handle with care.
Right.
And overall, they've shown that you can actually challenge this assumption that LLMs have to process information sequentially.
You can introduce a lot more parallelism without sacrificing performance.
And that's a big deal.
It is.
So what are some of the future research directions that this work opens up?
Well, they suggest several exciting possibilities.
Okay.
First, FFN Fusion could be a valuable tool for understanding how these models actually work.
For model interpretability.
Okay. Again, they're really interested in pushing the boundaries of parallelization even further.
With block parallelization.
Right.
Okay.
Third, they want to see if FFN Fusion can be applied to mixture of experts models.
Which could lead to even more efficiency gains.
Exactly.
And finally, they're really interested in exploring the relationship between model size and the potential for parallelization. So lots of exciting avenues for future research.
Yeah, there's a lot to explore.
Well, this has been a really fascinating deep dive into FFN fusion.
It has.
It's amazing how this research is challenging some of our core assumptions about how these models work, and it's giving us a really practical way to make them more efficient.
Yeah, it's a game changer.
Absolutely. And for anyone listening, I want you to think about the implications of this move towards more parallel processing within neural networks.
Yeah, it's a big shift.
Could FFN fusion inspire even more radical departures from traditional sequential designs?
An exciting possibility.
It really is. Maybe spend some time exploring puzzle framework or some of the other LLM optimization techniques we discussed.
That's a great idea.
And the biggest question of all is, could FFN fusion be a key that unlocks even more fundamental changes to the way we build and run these incredibly powerful models?
It's definitely a thought-provoking question.
It is. It makes you wonder what the future holds.
Yeah, the possibilities are endless.
Absolutely.